What should you do if a ladder is painted or has writing on it? And that would be take it damaged and store it.
Yep.
So this part's pretty good. Okay, so common numbers, 1.5 meters. So there's lots of references of 1.5 meters in the code book.
Yeah.
Right. So it's one of those common numbers that you should probably remember.
5 feet.
Yeah, 1.5 meters. Yeah, 5 feet. Now, you may see something where it's like, how close can a spoil pile be from a trench? And that would be 1 meter.
Right.
Right. But again, it depends on the soil. So if we have softer soils, we want to have it further away. You might see something similar where it says, okay, how close can machinery be to a trench? And again, that would be 1 meter, but we also have to, like I said, consider softer soils.
Right. So is there a difference between the softer soil length or?
Yeah. I mean, harder compacted soils, they're a lot stronger. So that's why if we look here, it's 30 degrees minimum for the cut-in angle if we're sloping it. But with softer soils, it has to be at 45 degrees.
Okay.
Now, this isn't exactly accurate. The numbers you need to remember, so like just like with the ladders, it's 1/4 the height.
Yeah.
With the sloping, it's 3 feet out, 4 feet down.
Yeah.
So we don't actually use this 5 foot thing. And the whole reason why is because if you think about it, most people in trades are what, over 5 feet, over 6 feet. Right. So we don't use 5 feet because what would happen if you were standing in that trench and it caved in? That would actually cover your lungs.
Right.
You wouldn't be able to breathe. So that's why we leave it to 4 feet.
That's it.
Yeah, and that way we're for sure going to be able to survive. Right?
Yeah. Yeah.
Part.
Well, that makes sense.
Yeah. So remember, it's a 3 or 4. So 3 feet out, 4 feet down.
3 feet out, 4 feet down.
Yeah.
Yeah.
A lot of these tables you don't have to really worry about. Now, confined space entry. So that's why this book is so important, is when we're dealing with confined space, what do we have to have? Well, we should have safe work procedures written out that can be checked, right?
Yeah.
We also have to check the OH&S, occupational health and safety, as to what we have to do. So if we're going into confined space, we might want to take air samples. And the other thing we want to make sure of too is that we have someone who's an alert person, someone who's standing outside of the confined space who can monitor when you go in it.
Right.
So that's why that's important. Now, again, flammable explosive substances. So we're dealing with any time you have a fire, you have to have the proper extinguisher. Okay, so like most of them are ABC. So A for ash, B for oil, C for circuitry, right?
Yeah.
D is the rare one. That's combustible metals. Okay, so we're not going to typically have those fire extinguishers around because we don't deal with combustible metals like sodium, potassium, things like that. Right. But we do deal with fuels. We do deal with paper products and cardboard and all sorts of other things, right? So part of the flammable and explosive substances, like even a B tank. There was actually one of my students years ago. He got off a job and left a B tank in his car, and I guess he left it open, and the torch was kind of leaking. And what ended up happening was he lived in an apartment building. So what he did in the morning was he came down, and from the front doors, he hit his car alarm. Well, because the gases were building up in his car overnight, his car exploded.
Holy.
Yeah. So you can imagine, hey, like you can go up to your car and it's like boom, it blew his car in half.
Oh, are they?
Yeah, so I mean that's why there's safe work procedures for when you're dealing with anything flammable or combustible or explosive.
Yeah, that's crazy. Those what do we carry? We carry B tanks in the back of our van. I hate
Yeah.
I hate that idea.
Well, as long as you take off your torches, you're fine.
Yeah, but we don't. Nobody does.
You know, well, it's no good.
That's a hazard.
It's no good.
No, not good.
Okay, so what else do we need here? Okay, so respirators, we've got to deal with the PDE, things like that. So apparently some of my students have told me that what they've seen on their tests is even just color codes. So like if you look at your work boots, you have the green triangle with the CSA.
Yeah.
And then you have the orange omega symbol.
Yeah, I've never seen that.
That just the omega symbol stands for electrical resistance.
So insulated.
Yeah, exactly.
Yeah,
So
I've actually never seen those bits around or anything.
and that's why we have to use class E hard hats now too, right? Because they're rated for up to 20,000 volts.
Right.
So you won't get electrocuted in your head.
Yeah.
Which is probably a good thing, right?
Yeah, for sure.
Yeah, and then what else are we looking for? Okay, so dust and fiber hazards. We know about that. Obviously, asbestos, silica, things like that. We need proper respirators. If it ever comes down to it, with the silica dust, a good thing to remember is it's the purple filters, and
Yeah.
then you have to get fit tested every year.
Yeah.
Right.
Clean shaven or something. Or...
Yeah. I mean, I always hated doing that. Right.
Yeah.
And then they stick this nasty smoke in your face to make sure it's working.
Yeah.
Right.
Yeah.
And yeah, even when I first started, silica hazards weren't even a thing back then.
No, I can imagine. No.
So yeah, we used to. All I was told when I first started as a first year was, just breathe out or look away from the dust. That's that's what I was told.
Yeah.
And then I find out,
Look at it now.
yeah, 4 or 5 years later, I find out, oh, silicas are a serious hazard, right?
Yeah.
And
Something about not disturbing or something was the key.
well, what happens apparently just like asbestos. So asbestos actually digs into your lung tissue.
Yeah.
And then it sits there because it has basically little barbs, and then it's sort of your body's trying to reject it, but it can't. So what happens is the skin inside your lungs kind of goes over it,
Right.
and then that's why cancer forms.
Ah.
Now with silica dust, that's a completely different thing. What happens with that, because it's so fine, it actually sits in your lung tissue, and because your lungs are basically wet, it actually forms a cement.
Oh, crazy.
Yeah,
It grows, builds on it.
yeah, and it builds up over time, right?
Crazy.
So that's why we have to worry about that. But that's in the OH&S stuff.
Right.
Okay, identification of piping systems. This is important too, sort of. Most of the stuff is for industrial applications.
Mm-hmm.
Okay, so if we were going to identify a sprinkler pipe, that would be red. If we were going to identify a gas pipe in industrial, that would be yellow. If we were going to identify process water piping, that would be green. So process water would be used to cool equipment, let's say. So it's not potable, but we're just cooling the equipment. And then we have blue pipe, which would be for potable. So the kinds of things that you might get are going to be in residential. What color is a gas line painted?
Yellow.
Actually,
or gray.
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 Yeah, in residential.
Yeah.
Yeah, in industrial, it'd be painted yellow.
Yellow. That's right.
That makes it obvious, right?
Yeah.
What else do we need from this guy? Okay, steam traps. I think they've mostly removed steam. from your test. Now, how are you with this?
If I look at it, I remember it, but I always have to come back to it, like weighting and all that stuff.
Okay, so
And
if
then even some of the conversions, I try to teach my kids that from Celsius to Fahrenheit and all that.
right, so this actually uses 9/5 or 5/9. So I wouldn't use those numbers.
No,
What I
isn't
would-
it 1.8 or something like that?
Exactly, yeah, 1.8.
Yeah,
So I would do Celsius times 1.8 plus 32 degrees to get Fahrenheit.
yeah,
For Fahrenheit, I would do minus 32 and divide by 1.8,
right.
right?
Yeah.
Now, here's the issue too. So we always have imperial and we have metric, right? So Fahrenheit would be imperial or US, whatever you want to say, and Celsius would be metric. When we're doing calculations, like with the combined gas law,
hmm
we always have to have absolutes. So we always need absolute pressure and absolute temperature, right? So hopefully you don't get any questions like that, but
I
easiest.
remember one or two, and I did study a lot on it because it was interesting to me.
Do you remember the formulas?
Yeah,
Okay, so it's V initial P initial divided by T initial, or you can do V1 P1 T1
right,
equals V2 P2 T2,
right.
or final. There's a lot of different ways you can say it. But with those, we need absolute pressures and absolute temperatures. So if we want absolute pressures, what do we do?
I use 14.69.
14.7, yeah.
With that one, yeah.
And then what do we add that to?
Oh, the temperature, I believe.
No, we're dealing pressure.
Okay. You lost me then.
Okay, so if we have 14.7 psi, which is standard atmospheric pressure,
Mm-hmm.
what would we add that to get absolute pressure?
Mm, Jeez, I can't remember. Is that something to do with our province?
Yep. So hang on, I'll show you.
You guys, 13 point something.
Okay, so if we are looking at, let me just find a picture here. Sure, that works. Let's see. Just gonna find me a picture here.
You know, while you're doing that, I was just thinking, like, what kind of work would I be doing if I have to deal with absolute pressure all the time? So, like pumps and
Well, here's the thing. You don't have to deal with it all the time. But you do need to know about it because you may get a question about it.
right.
Right? So you've installed these gauges a whole bunch of times, right?
Yeah.
Okay. So if we notice on the bottom here, there's a little hole.
Mm-hmm.
Okay, but the gauge reads 0.
Yeah.
But there's still atmospheric pressure inside of the gauge. But just because the gauge is zeroed means that we don't include that.
Right. So it's built into it.
Yeah, so absolute would be the gauge pressure plus atmospheric pressure,
Oh, okay.
and that would be absolute, right? Because again, what's acting on this right now is atmospheric pressure,
Right.
but the gauge reads 0.
Okay. So as soon as something's in there, that's gauge pressure.
Exactly, yeah. So for doing the combined gas laws and things like that, we have to take the gauge pressure and we have to add it to the local atmospheric pressure. And that gives us absolute, because the only way to do that calculation is with absolute pressure.
Okay. So that's that plus 14.7.
Right, 14.7, yeah. Now with temperature, Fahrenheit, the absolute for temperature for Fahrenheit is Rankine, and the absolute temperature for Celsius is Kelvin. So the numbers that are important to remember is 460 for Fahrenheit to Rankine, and 273 from Celsius to Kelvin.
Okay. At absolute zero.
Right. So this, if you look down here, Fahrenheit is negative, basically 460 degrees Fahrenheit, but absolute in Rankine is 0. So when we're dealing with temperature, absolute 0. So even space has energy, right? It has a little bit higher of a temperature than 0, right? It's probably, I would say, maybe 20 degrees Rankine, somewhere in there.
So it'd be just above or something.
Just above absolute 0.
Right.
Because the problem is once we get to absolute 0, that means there's no energy in the atoms. They fall apart. So scientists have been able to get it down to about 1/10 of a degree from absolute 0, but never absolute 0 because everything contains energy.
Right.
Right. So yeah, like I said, the numbers you just need to remember are Fahrenheit to Rankine plus 460, Celsius to Kelvin plus 273. Okay. So yeah, make sure you keep track of that. And again, those are just for combined gas laws calculations.
Right.
Hanger spacing. So hanger spacing, what we want to do is we want to go to 2345 or 2344. So in the code book, 2344 talks about vertical spacing. So it's every other floor, maximum 7.5 meters, which is about 25 feet. And then for horizontal piping, we want to do 2345, right? And then we want to check for the type of piping we're using and then figure out our calculations from there.
Right.
Okay. Rod diameters, same thing. Go to the code book. Don't use this because there's no need to. U-bolts, we don't have to worry about. Tables, we don't have to worry about because if you're given any tables, it's just going to be a basic thing they ask you.
Okay.
Twist drills, no. This is good. Okay, so this talks about threads per inch. Right, so this is definitely a need to know.
Okay.
So with 1/8 is 27 threads per inch, quarter to 3/8, 18 threads per inch, half and 3/4, 14 threads per inch, 1 to 2, 11.5, and then 2.5 and above is 8. Now, what's important about this is the type of questions you're going to get, possibly, are which dies can handle which thread sizes. In other words, the answers are going to be something like, can I go 1/2 to 1.5 inches with the same dies? That's going to be A. Can I go 1 inch to 2 inch with the same dies? Can I go 1.5 to 2.5 with the same dies? Or can I go 1/8 to 3/4 with the same dies?
Okay.
Right. So obviously, because there's more threads per inch, the smaller we get, the right answer for that kind of question would be 1 to 2. We don't have to change the dies.
Okay.
But my other examples, so like 1/2 to 1.5 inches, yeah, we'd have to change the dies because they're different threads.
Right.
Right. So even 1.5 inches to 2.5 or 1/2 to 2.5, we'd have to change the dies 3 times. Right. So that's not going to be the right answer.
Right.
So that's why this is important, because you may also see a simpler question. That's going to be how many threads per inch for an 1.25 inch pipe?
11.
11.5. Right.
Yeah.
Might also ask you what the thread pitch is. So the thread pitch on any standard pipe thread is 60 degrees.
Okay.
Right. Now, here's some good formulas. The ones you want to know how to do would be square rectangle, circle, cylinder, cube. And that's about it.
Okay.
Now, with all these tables, the numbers are good to know. So if you actually go on my formulas page, did you print that off?
I could, yeah.
Yeah, so it's probably a good idea to do that with all the properties of water and all the formulas on there, and then just add to it.
Okay.
Right? So with these tables, they talk about scientific notation, which is what this is. Right? This 10 to the power of 6. So all this basically means is we're adding 6 zeros to this number.
Right.
This one we're adding 5.
Right.
If it has a minus in front of it, that means we're taking the decimal and moving it 5 spaces to the left.
So that's 0.00.
Yeah, so this would be 0.000000254.
Okay.
So that's why they did this, and I think they did that too to condense the table a little bit. But some of the ones you want to know is obviously meters to millimeters, 1,000. Meters to centimeters, 100. The other one, I would say too, is decimeters. So how many centimeters per decimeter?
Like the 0.01?
Well, no, it would be, so if we had meters to decimeters.
Oh, to decimeters. Yeah.
Yeah,
So,
that would be 10, right?
yeah. In between centimeters and meters.
That's right. Yeah. So we had decimeter in between. So it would be 10 decimeters per meter, 100 centimeters. So you can see that we moved the decimal, or we just adding a 0.
Right.
Right.
Yeah.
So those are good ones to know, especially when we're doing rainfall, because we have to know it's a 1 square meter area, and then there's 1,000 millimeters per meter. Right.
Oh, okay. Yeah. I see what you mean.
Yeah, and the code book actually talks about how we calculate for liters. So it's 1 square meter, 1 millimeter high equals 1 liter.
Yeah, because would they ever give the answers in a different value?
No, it would always be metric. It'd always be liters. And the
Okay.
reason why is because we have to use liters to use the tables.
Right.
Right. So these are good ones. Meters, millimeters, meters, centimeters. What else is good? Feet and inches, right? So obviously 12 inches per foot.
Yeah.
And then if you look down here, when we go to square feet to square inches, what we're doing is, because it's squared, we have that number 2 in the back of it. All you'd have to do is just sit there and think, okay, well, that's 2-dimensional. So if 1 foot is 12 inches, 1 foot by 1 foot would be 1 square foot, but 12 times 12 will be 144 square inches.
Right.
So there's ways you can figure it out. And the best thing to do when you're doing conversions like that is draw it.
We draw the square.
Yeah, draw the square, draw the cube, draw the line.
Okay.
Yeah. So there's lots of numbers on here, but like I said, I would look at the properties of water and then look at that formulas page, because it has the properties on there too. And then converting from metric to imperial, it's always a little bit different, a little bit difficult. But if we look here, cubic feet, cubic inches, so 1728 cubic inches per cubic foot. So again, draw the cube, 1 foot, 1 foot, 1 foot, 12, 12, 12. Right? So where the 1728 comes from is 12 times 12 times 12.
Okay.
Yeah.
Makes sense.
Yeah, and these ones are good too. Now, these aren't the exact numbers. They went a whole lot of decimal places past where they needed to. Same with this. So if 1 cubic foot, how many US gallons in a cubic foot? I would just say 7.48.
Right.
Close enough. Imperial gallons per cubic foot, I would say 6.23 or 6.24.
Right.
So it's things like that you want to pay attention to, and definitely do the numbers. Here, okay, so here's the pressure calculations. So this is where it talks about standard atmospheric pressure in different units. This is where we get the 14.7 from. We're just rounding up to the first decimal.
Right.
Inches of mercury, I would just round that up to 30. Close enough. And then here, what it shows is, again, absolute pressure, gauge pressure, plus local atmospheric pressure. Right, so it visually shows you how we calculate it. So let's say on our gauge pressure we have 10 psi, and then local atmospheric, let's just use 14.7. So what would absolute pressure be?
Would be that plus the gauge. If we had 3, you said?
So we have 10 psi gauge pressure.
With 10 plus 14.7.
That's right.
That's 24.7.
There we go.
What's the differential pressure?
Good question. Okay, so have you ever tested a backflow?
A backflow? No.
No, did you ever have to do that in school?
No.
Okay, so what differential pressure is saying, okay, so what is the pressure difference between this pressure and this pressure? So let's say we have 30 pounds here and we have 10 pounds here. What would the differential pressure be?
30 pounds.
30 how much?
30 pounds?
Nope, we have 30 at the top and 10 at the bottom.
Oh, 20.
20 pounds. Yeah.
Okay.
That's differential. Just measuring two different.
So between pressure and atmospheric pressure.
Yeah, if we're just talking gauge pressure, it would just be a gauge pressure minus a gauge pressure. If we're going absolute, then we'd have to include atmospheric pressure to figure that out. All right.
So you could say that anytime. What's the differential?
Yeah, exactly.
Okay.
So that's how we pressure test backflow preventers.
Okay.
So if we're testing across the check valves in a DCVA or an RP, we use a differential pressure gauge. We attach the hoses to the test cocks, and then we read the pressure that's going in and then that's coming out of the check valve.
Okay, so then you just calculate the difference.
The gauge does it for us.
Oh, okay.
Yeah, so we just read it, make sure it's above a certain point. With check valves, it has to be at least more than 1 psi. Right? So let's say on the supply, we have 100 psi. In the intermediate portion, if we don't have more than, or if we don't have less than 99 psi, then there's a problem. That means that check valve is either fouled or it's stuck open.
Okay.
Works for you?
Works for me.
Nice. PSI to KPA. We don't want to use this number here. What we want to use is this number here. So there's, again, I would just go to the third. So it's 6.895 kPa per PSI.
Right.
If we're doing that conversion.
Yeah, and we deal a lot with that with our water.
That's right. Yeah. Yeah. Now, because we're dealing with the plumbing code, obviously it's Canadian, so it's metric.
Yeah.
So what it says in there, dealing with plumbing fixtures, is that the maximum you can have to a plumbing fixture is 550 kPa. So if we were going to convert that to PSI, what do you think we would do?
So divide it by that. Right. 6.895.
Exactly right.
Okay.
Yeah, just that simple.
Right. I just always remember some kPa like that 9.83 for pressure, for water pressure. Right.
And what's that for?
I believe that was for calculating elevation.
That's right. Good.
Yeah.
Yeah. So it's 9.8 I think it's 9.81 kPa per meter.
Right.
Right, and that's how you do that.
With that.
Here are your other two numbers. So 0.433 psi per foot, or 2.31 feet per psi.
Okay.
Right. So here it gives us a formula. So the height in feet equals the pressure divided by 0.433. This would be psi per foot, times the relative density of the liquid. So obviously water is 1, so we just multiply it by 1.
Right.
Which is why we don't even consider it. But if we're dealing with gas, which is obviously less dense than water, then we have to put the relative density of the liquid, of the gas, in the equation too, to get the pressure at the base.
Yeah, I don't ever remember seeing that much of that formula.
In your test, you do have to do these kinds of calculations.
Yeah.
So
I'm just trying to think like other formulas, like for probably like hydronics or something else.
well, with those, typically what they do is they give you the formula sheets for them. So you might get an air conditioner question where it says calculate how many tons of AC we need. You might get a hydronics question where it says, okay, turn BTUs into flow rate and GPM.
Right.
Right. So most of those, they're at least going to give you something for it. But we'll definitely have the opportunity to go through that.
Yeah, for sure.
Okay.
Okay.
And that's it for that guy.
Yeah.
It's not too bad, is it?
Nope.
So,
I'm doing welding right now, and I was just like, oh my God.
what's wrong with welding?
Oh, I should have been a welder.
Welding isn't bad.
No, I've never done it.
I haven't either, even though my old man apparently was a welder.
Yeah.
Yeah, I've never talked to him. Well, I think I've talked to him 3 times in my life. But yeah, so he was a welder, but he was a welder back in the 60s and 70s, right?
Yeah.
And again, back then, safety wasn't a thing.
No.
Not as much as it is now.
Yeah, the book is increased by like 5 pages, I think.
Now, with this is the kind of stuff you want to pay attention to, is shade numbers, but not remembering the shade number. It's more of understanding that the lower the number, the lighter it is.
Okay.
So if
Higher the shade,
yeah, the higher the number, the heavier the shade.
Right.
So like when there was a solar eclipse here probably about 10, 12 years ago.
Yeah.
And I was in school at the time. I think I was in level 2. And what we did was we actually took welding goggles so we could look at solar eclipses right at the sun.
Sweet.
Yeah, it was pretty cool.
Yeah.
So yeah, stuff like that. Ventilation obviously is important. How you connect oxygen and acetylene cylinders, this is important. What the maximum pressure for acetylene is also important.
Yeah.
The connection type for the regulators, also important.
Yeah.
Right. So if you, like, for instance, if you see a notch in the nut for an acetylene regulator, what does that tell you?
Between the mixture of oxygen?
No.
No.
It's just a line notched into the nut.
Line notched into the nut.
Yeah.
Is that not what acetylene means?
Yeah. I'll show you just one second. Cylinder. Regulator. Okay, so images. Okay, that's a good one. Okay, so, well, it's kind of a bad picture, but you see these little notches in here?
Yeah.
Better
Oh,
picture.
left-handed thread.
There you go.
Yeah, sorry.
There you go. Right, and they're male.
Yeah,
And then these ones are female, right?
female.
The oxygen. So
Yeah,
that way you can't attach an acetylene regulator to an oxygen tank,
right.
right? So you may see things like that.
Yeah,
So always looking up the pictures.
yeah, I'm more of a visual.
Yeah, exactly. Yeah. So I did it. Um, and then procedures. So you remember what I told you with procedures?
Yeah, so they probably throw us somewhere in the middle and try to figure out their steps.
Exactly. Yeah. So even though like this is 11 steps for setting it up, they may only give you in the answers, they may only give you 4 or 5.
Right.
So that's why it's a good idea to write this out on your own, in your own words, so that you understand what the proper procedures are.
Yeah, just go through it.
Yeah. Yeah. Also, simple things like what color are the hoses?
Right. Red for acetylene and green for oxygen.
Exactly. If I ask you a question about, okay, how do we transport cylinders? What do
Right.
we have to do?
Off the top of my head, you have to strap them down. I
Right?
think the cover needs to be on the cap. Needs
Yeah.
to be on, and then
Exactly. So that's the type of questions you're going to get.
Right.
It could be a variety of different questions like that. Like, how do we secure cylinders? We strap them down. If we're
Right.
transporting them, we have to cap them and strap them down. Right?
Yeah.
Things like that. But the procedures definitely want to write out on your own.
Okay.
Same thing with like lighting a torch, shutting down the oxyacetylene equipment.
Right.
Balancing. So the balancing, all you really need to know about that is the different types of flames that you could get.
Like the tip, like the ends there in that picture.
Yeah, the flame types. So if there's too much acetylene, what do we have? We have a carbonizing flame.
Right.
At a proper mix ratio, you'd have a neutral flame. And if we have too much oxygen, we have an oxidizing flame.
Okay.
Right. So it's just simple things like that.
Right.
And then weld symbols. Okay, that's the next important one here. So from what I know, from what I've heard, the ones that are good to know is the flag and the circle.
Is it a dot you mean, or circle, like a highlighted circle?
Yeah, the circle right here.
Okay.
So the circle here, like, let's say you get this image without all the writing, and it says, okay, what does this indicate? So the flag would be a field weld,
Okay.
meaning that a welder would have to go and weld this in the field as opposed to a shop.
Ah, gotcha.
And then the circle means weld all around. So that means basically that you're not putting fillet welds. You're welding possibly a butt weld on the top. You're welding from underneath. You just want to make sure it's all around.
Okay.
Okay.
Could have been a welder.
Could have been a welder, yeah. Positions, that's important. So you may get something that has the number, right? So the more important one is actually here. So you may get a question where it says you have an E61-2 rod.
Okay.
So what position can I weld that in? And that would be all positions, right? Because the third number is 1.
Yeah.
So that means all positions.
So the third number on that labeling is telling you the position of the weld.
Right. The first 2 numbers talk about the tensile strength. So if, let's say we have an E7018, let's just use that as an example.
Yeah.
That would mean that the weld would be able to handle 70,000 PSI.
Okay.
What positions? Well, it's a 70-18, so that means I can weld it in all positions.
Yeah.
Because I have number 1.
Right.
Okay. So that's definitely something to remember. The other thing you want to remember is which rods need to be kept in an oven. And whatever answer says something to the effect of low hydrogen, that's the one you pick.
Low hydrogen.
Yeah.
Okay.
And I believe those ones are the E70-18s.
With the 8 on the end, is that what that means? Or
No. The eight means something else. So yeah, so the 8 could indicate polarities. It could also indicate use.
Oh, okay. Of like where?
Yeah, exactly. Or what type of system.
Okay.
Right. So that's always another number. But the ones you definitely want to know is the first 2 and then the third one.
Okay.
Right. And then the ones you need to keep in an oven would be low hydrogen.
Okay. So yeah, first 2 is the pressure, and the third one is the where positioning, and the last one is whatever.
Yeah.
You were saying what was the material again?
Well, that would be
Low
yeah, low hydrogen. You want to keep in an oven.
oven.
Make sure it stays dry so the coating doesn't come off.
Okay.
You need that coating to maintain sort of like an oxygen-free environment when you're welding. You may see, so stuff like this is important because you may see something to the effect of what welding process would be used for stainless steel pipe. And that would be gas tungsten arc welding, GTAW.
Okay.
And then it walks you through how it works, which is fine. Oh, this is good right here. So pipe prep. So if you're ever on the job and you're working with a welder, and he's like, okay, grind the bevel and leave me a land. So what a land refers to is the straight portion on the edge of it. The welding bevel, you want to remember, is 37.5 degrees.
Okay.
Okay, so it's 37.5 degrees with either a 1/16 to 1/8 land.
And what's the example? Like if you ever
If you're ever working with a welder, so like
Yeah.
I've worked up north, like I worked in the Yukon,
Yeah.
and we were doing basically process piping for a mill building,
Yeah.
right? So they were extracting gold and platinum and all sorts of other things,
Mm-hmm.
right? So working with a welder, I had to bevel the pipe so I could just give it to him and then he could weld it,
Right.
right? So he wasn't as picky as that. So he said to me, he's like, okay, well, 45 works, whatever, but just make sure that I have a 1/16 to 1/8 land, which is the straight portion.
Yeah.
So he could do his fit up.
Okay.
And I'm like, okay, sure. But this would be strict if it comes to a test.
Okay.
Right? So just remember welding bevel, 37.5
37.5 inches.
degrees.
Sorry.
Degrees. Yeah.
Bevel. Yeah.
Yeah. And then the rest of the stuff, I wouldn't worry too much about. How many tacks do you need? 4. Very simple. What would you use to line up pipes? Well, it's a
Right
what is
angle.
it? A square.
Hey.
And then okay, this is important. So with flanges, we never want one hole on the top. It's always 2 holes. And exactly for this reason, so we can level off the flange.
Okay.
And then what we want to do is just like this, we want to use a square, measure off the pipe to make sure that it's actually angularly proper.
Ah.